Now, information of colored ions, again, the explanation will simply be based on what happens to the d orbitals. So let us just see what is here on the first slide. So placing ligands around a central ion causes the energies of the d orbitals to change. We will be able to see this in the next slides. Some of the d orbitals gain energy and some lose energy. We will be able to see this pictorially. In an octahedral complex, two of those orbitals, say there, go to higher and three go to lower energy. I will show you that in the next slide. In the tetrahedral complex, the three orbitals go higher and the two go lower. We'll see that in the next slides. Now, the degree of splitting depends on the central ion and the ligand. The energy difference between the levels affects how much energy is absorbed when an electron is promoted. The amount of energy governs the color of light absorbed. I think we'll be able, and if you go back to your notes, you will see in very simple form what is involved in the formation of colored ions. Okay, so to just look in terms of orbitals, now you see, we said we can explain everything that happens in terms of what happens to the 3D orbitals, okay? Now, for the octahedral case, the split in the energy levels of the d orbitals is that two orbitals are split to a higher energy level and three to a lower energy level. The idea is that when you have your metal ion, okay, it can only form a colored ion if it is a cation. That means it is charged. So, for example, in this case, we are taking an ion which has this 3D electron configuration. So you can imagine a ligand in the vicinity of an ion which has this 3D configuration. What will happen is the 3D will split and the electron arrangements will be as arranged after the split here, okay? So these are the two, what we are talking about. The Z square and the XY will go to a level, and the other ones will go to the lower energy level. Okay. So if you look at the tetrahedral one, the split is opposite. For tetrahedral splitting, the three go to a higher energy level and two come to the lower energy level. So let's see what happens. Okay, we are considering a copper free ion. This is the 3 orbital, the d orbital of a copper 2+. When a ligand approaches, the d orbital splits to 2 orbitals of higher energy level and 3 orbitals of lower energy level. Now the d orbital electrons must be arranged in the split, okay? So for this case, one electron can be excited to go to fill this one up here. In the process of doing that, energy is given out, or energy is absorbed by this electron down here to be able to go to the higher energy level. So we talk about an energy difference. Simply put, is that for a particular element, you have the ligands approaching the ion. That causes the d orbitals to split to two energy levels. Now the two energy levels, there is a possibility of an electron being excited to a higher energy level. That energy excitement is associated with a particular wavelength that will give us the color that we will observe when that transition occurs. So the observed color of a solution depends on the wavelengths absorbed. Copper sulfate solution appears blue because the energy absorbed corresponds to red and yellow wavelength. Again, we'll be able to see that. We usually only see, okay, it says there are wavelengths corresponding to blue light aren't absorbed. So we usually just see what is reflected, okay? We'll be able to explain that a little more. Energy corresponding to these colors is absorbed. Okay, now this is not very straight here. But if violet is absorbed, one will see the reflected ones, which will appear as green or yellow. If blue is absorbed, one will see yellow. If blue is absorbed, then one will see red, because that is what is reflected. So we only see what is reflected. What is absorbed to excite the electron from a lower energy level to a higher energy level is not observed, okay? So the observed color of a solution depends on the wavelengths absorbed, okay? So if you take normal white color, normal light that we are seeing, and our copper sulfate is blue, okay? What you will be seeing is blue and probably green, which are not absorbed by the blue solution that you are seeing. So white light goes in and the solution appears blue, because blue is what is reflected by the color of the colored ion. So a solution of copper sulfate is blue because the red and yellow wavelengths are absorbed. So what you are actually seeing is reflected is at the wavelength around here. So the color observed in a compound or complex is actually the complementary color of the color absorbed, okay? So if you absorb orange color, one will actually see blue color. So this is called a complementary color chart, okay? So if you actually absorb blue, then one will absorb orange. One will observe orange. If you absorb yellow, if yellow is absorbed by your solution, then one will actually see violet, okay? And vice versa.